Hi everyone, this is another video of the Polymer Reaction Engineering series. In the previous video, we have seen the features of the two main polymerization mechanisms, so step and chain polymerization. In this video, we will compare some of the polymerizations that belong to the step and chain groups, along with some of their characteristics. Finally, we'll have a look at how much polymer is being produced today, quantifying the relevance of each mechanism. So let's get started. We saw already the division in step and chain growth, but which other further subcategories exist beyond that? Well, so step growth can be further distinguished in polycondensation and polyaddition, whereas the main mechanisms of chain growth are radical, anionic, cationic, and, drumroll, coordination polymerization. So let's have a look at them, and starting with step growth and a general reminder of how it works. For more details, you can find a video linked in the description, but let's keep it brief now. Okay, so step growth is characterized by the fact that any two chains can react together if, of course, their functional groups can, all molecules grow at the same time, and average chain length increases slowly with functional group conversion. Do you remember the lonely dimer in an ocean of monomer we made an example of? Anyway, to exemplify this, what we did is that we took a molecule with two A functional groups, reacting with one having two B functional groups, forming a link L between the two monomers and releasing a molecule R. We also saw a general formalism where two polymer chains, which we create fantasy called P, okay, of length N and M, react together and form a longer chain of length N plus M, and a group which was being released in this reaction R. Let us have a look at polycondensation now, which is, as we said, one of the two main forms of step growth polymerization. So the differentiator, spoiler alert here, is the equilibrium. So in polycondensation, the two functional groups of the two monomer or polymer molecules react, releasing a small molecule in an equilibrium reaction. Okay, it could be water, it could be methanol. Let us consider polyamides. Okay, one way to form them is to start with a dicarboxylic acid. So here, adipic acid, which has two COOH groups. Remember, in our sketch formalisms, these COOH groups were the two A groups. Okay, and then we also need a diamine, here hexamethylene diamine, with two NH2 bonds. In our sketch, the two Bs. Okay, when the two monomers react, they form a CO-NH bond, which is the L linkage, and release a water molecule. The reaction is at equilibrium. This is very important. While at the very beginning, we have no water, after converting monomers to form these first short oligomers, dimers and trimers, we will also have enough water around that the reverse reaction occurs. So we fail here, right? We want to polymerize, we want to have larger and larger chains, but well, dimers and trimers, if there is too much water, they will start depolymerizing, okay, to their smaller building blocks. So if we don't remove water from the reactor, we will not obtain polymers with large molecular weights remaining with oligomers. Okay, so in fact, the equilibrium limited nature of polycondensation plays a major role in reactor design and operation. Okay, of course, beyond the reactor that you have at the beginning, you need to find a way in your process to drive the separation, really, okay, of the released small molecules to drive the reaction towards the products, for instance, by evaporation. However, this then in turns a way to recover the monomers because of their volatility, otherwise we lose too many of them, okay? So do you start to get the intricacy behind this apparently simple reaction? So this was polycondensation. Now let us look at polyadditions. This is the other main subcategory of step growth polymerizations, and these are not at equilibrium. So we have again two functional groups that react and form a linkage without releasing small molecules. Then again, we need some A and B groups. Okay, as we said before, this is the same principle. It's still step growth. And they will form an L group. Okay, so let us make an example on polyurethanes. We start So what do we need? We need one diisocyanate and one diol. A diisocyanate is a molecule with two NCO groups, and a diol molecule has two OH groups. Now, look at this. This is interesting. A and B, the groups A and B this time, represent completely different things. Okay? But this is the beauty behind this versatile formalism. As long as the chemistry works and A and B react together, the formalism can be used. So anyway, in this case, with NCO and OH groups, you get an NHCOO polymer linkage. Okay, the first step of a polyurethane. But is this the same as with polyamides? Yet again, a rhetorical question, because of course, no. But it's important to ask this question. Unlike polycondensation, polyaddition is not equilibrium limited and very exothermal. So here heat removal is really crucial as opposed to polycondensations, where heat and or vacuum is needed to remove the small molecules released and to drive the reaction, which is typically endothermic. Okay? So now let us switch gears. What about chain growth? Again, let us start with a recap. So only chains with active sites, radicals, ions, grow. Only them, no one else. Many other reactions can occur. Okay, so for instance, we need the initiation of active sites and their termination occurs as well. 3 very long polymer chains may be observed at low monomer conversions, so large viscosities are attained from the very beginning. Again, here we found a formalism that we decided to write as Pn star, where the star is the active site of this polymer chain P of length N, and by adding a monomer M, we have a longer, still active polymer chain of length N plus 1. Okay? So there are, of course, many types, very many types of chain growth polymerization, but here we will consider our 4 main categories for now are radical, anionic, cationic, and coordination polymerization. Let us start with radical polymerization. So the process is obviously, as the word suggests, mediated by, you guessed it, radicals, so molecules with an unpaired electron. They are formed in an initiation reaction. That, as the name suggests, again, it's quite telling, starts everything. So once a radical is formed, here we have this, small black rod with a small sphere. This attacks the blue, in our sketch, of course, electron-rich double bond of the monomer. And then we have a polymer chain of length 1. Okay? Then this one attacks the next monomer. Okay? And so the propagation, we formed a dimer. But this dimer is still active, and so the propagation can go on. We can have repeated attacks of monomers, and it goes on and on until, well, the radical terminates, or in other terms, dies. Radicals might have a great life, but boy, is it short. Typically, only a millisecond or even less. And still, in some cases, they manage to mediate the addition of thousands of monomers in their lifetime. That's kind of, 1,000 before they die. 1,000 monomers are being added by the same radical. So what does this mean at long chains? That's why, long chains can exist from the very beginning of the reaction. Okay? So the lifetime of active chains is crucial since it affects the length of polymer chains. If the radicals live little time, well, then the chains will be short. Or, of course, if they live a lot, they will be longer, right? And why is this relevant? As we saw in a previous video, this, by the way, is how you typically schematize this termination. So you combine these two molecules together, and the two active sites on each of them terminate, die, disappear, right? But why is this relevant? We saw in the previous video that the chain length controls many properties of the polymer. See how viscous they are, how resistant, okay? So that's why it's very important to understand the lifetimes, we'll see later on, of these chains, okay? So anyway, initiation, propagation, and termination, they repeat continuously throughout the polymerization process. Of course, many more reactions, may occur, but this is a story for another time. Now, let us switch to anionic or cationic polymerization, where the active species is an ion. We will deal with them together. In both cases, we will need, again, an initiation step. Okay? The initiators are, well, negatively charged if we are considering an anionic polymerization, or positively charged, obviously, right? In a cationic polymerization, that's not a big surprise. So you could have methyl lithium, for example, as an anionic initiator, or Lewis acids as examples of cationic initiators. So which monomers can be polymerized? That depends on their electronic structure. In anionic polymerization, we need monomers that contain electron withdrawing groups, meaning groups that can stabilize the negative charge introduced by the initiator, usually through resonance. Styrene there is a classic example. The aromatic ring of styrene can delocalize, okay, the negative charge. In cationic polymerization, on the other hand, we need monomers with electron donating groups. Okay, after initiation, the propagating chain, carries a positive charge, so it must be stabilized as well. Isobutylene is a typical example of a monomer that can stabilize a carbocation. The lifetime of the active chain is, it is very different in these two mechanisms. In anionic polymerization, if no impurities are present, the chains are essentially immortal. There's no natural termination step. Okay, only traces of water, oxygen, or other proton donors can induce termination. Under clean condition, the active chains can survive for hours, days, and in extreme cases, even months or years. Whereas in cationic polymerization, the active chain centers, the active centers, live much less. Carbocations are far less stable than carboanions and undergo rapid side reactions. So, the lifetime of their chains is much shorter. Given the big difference in chain lifetime, we can expect significant differences in terms of chain length distribution of polymers synthesized with the different techniques, right? Radical, anionic, cationic, but this is yet again another story. One final note on ionic polymerization: it is typically carried out at much lower temperatures than radical polymerizations. At higher temperatures, ionic centers would be too unstable and then undergo just some unwanted side reactions or terminate too quickly. Now, the last item on our list here, coordination polymerization. Here, it's a catalyst that actually mediates the initiation and the insertion, so the propagation of monomers into the growing polymer chain. This is often a heterogeneous process. So we can imagine that polymer chains grow from the catalyst surface, and the monomers insert at the metal carbon bond, with the metal catalyst mediating the process, extending the chain by 1 unit. Why this apparent overcomplication? Right, catalysts are messy. Of course, we can operate probably at lower temperatures, right, as you might have guessed, but there are also issues, right? Catalyst poisoning, diffusion limitations. However, we get stereoregular polymers, okay? So this polymerization, right, gives us isotactic and syndiotactic polymers, okay? And this is something which we discussed in the first video of our series. These polymers have much better mechanical properties than their atactic counterparts, okay? And even more importantly, some monomers like ethylene and propylene, which make up the vast majority of all polymers produced, they simply do not polymerize by standard radical polymerization. So coordination catalysis is what makes these massive industrial polymers possible. Now, speaking of polymer production, here I have adapted a visual from the Plastic Fast Facts Report 2025, which reports data from 2024, in case you're asking or wondering. You'll find the reference linked in the video description. So in 2024, global plastic production reached a staggering 430 million tons. And during the time, it took you to watch this video up to this point, roughly 12,000 tons were produced. 12,000 tons, and we were just sitting here. Anyway, this trend has been growing for decades. In a separate video, if you're interested, we can discuss the environmental implications and the state of recycling. But here I want to focus on which polymerization mechanisms are responsible for producing these materials. So the numbers you can see here, these percentages are approximate. Okay, I needed to make a few assumptions while rearranging the data, but the overall picture is quite clear. Okay, about 2/3 of all polymers produced globally come from chain growth processes. You see here 65, 66%. Okay, mainly coordination and radical polymerization. 25% come from step growth polymerization, and only 10% are recycled or come from circular sources. Now, among the chain growth mechanisms, as said, coordination polymerization dominates, accounting for roughly 40% of all polymer production, and radical polymerization accounts for another 20%. And again, 12,000 tons. Crazy, right? Anyway, let's move on to our recap. So in this video, we have seen polymerization types belonging to the two main classes, step and chain growth. Okay, we saw some essential features of them. Polycondensation is the one which is, equilibrium limited, which is quite, as we saw, a relevant aspect. Both polyaddition and polycondensation, as they are step growth, we know these are mediated by functional groups. They do not need any type of initiation. Conversely, the subtypes of chain growth need help to start, whether it's a radical or an ion, positive or negative, or a catalyst. Something needs to start the reaction and support propagation. Okay, on the active chains propagate. Do you remember? We discussed about the different lifetime of the chains and saw how only coordination polymerization offers a way to produce serorregular polymers. Finally, we quantify the relevance of the mechanisms with respect to the total plastic produced and saw that chain growth dominates. Well, that's all for now. If you like the video, have comments or questions, I would be happy to hear from you. See you next time.